Engineering 305, example problem 8-12. We have another cantilever beam problem we're going to solve through cartoons. This one, the other one was simply supported. This is a cantilever beam. This is 5 meters long. It has a uniformly distributed load of 7.5 kilonewtons per meter and a concentrated load of 25 kilonewtons as shown in figure 821, which I've got the picture there. We've got steel, 28 GPa. You know, I know they want it, yep. Steel, 28 GPa. The beam is a wide flange section, which really doesn't matter because we just need I, which is equal to 500 times 10 to the negative 6 meters to the fourth. Determine the deflection at the right end of the beam. So I'm just going to say we've got the picture. That's what's important. And then the other details that I guess I want to say is EI is a given, so we don't need to sweat that anymore. So the first thing I want to do is take a look at, okay, there's our picture, and typically what I am going to do as I solve these is I'm going to say, look, here's my situation, and I'm going to have a load out on the end, and I'm going to have a distributed load the whole way. And because I get to use colors, and I would do this in the classroom on the board, I would use the red marker. I get to put things in colors. Now, the key for superposition is you're going to superimpose loads on top of each other that the loads can add. So when you look at a problem like this, you should say, well, I need to separate out my loads. And so this situation becomes a cantilever beam with a distributed load and a cantilever beam with a point load. You get those two loading situations on top of, put together, and that's what our load consists of. Oh, that's not what I wanted. Move that over there. So now we simply have to go look at our cartoons and go, do we have cartoons for those things? Well, turn that off, turn that on. Sure enough, we do. If you look at, do we have situation 1? Not really. We really have a situation where the load is inboard a little bit, but situation 1 might help us. And actually, that's what we're going to wind up using. And we have situation 2. Okay, so we need those equations. We're going to wind up popping back and forth. Let's look at our problem statement a sec. Determine the deflection at the right end of the beam. Well, since I don't have, that's easy for the second case, or for the distributed load, the second case. If I look at that equation, the distributed load, the deflection at the end is minus, I'm going to write it on, delta is equal to minus WL to the fourth over 8EI. And that's good for that one. What do I do with my cantilever beam? Well, I'm going to say we need to look at that cantilever beam a little bit differently. We're going to look at that cantilever beam like this. And then, well, maybe that's not the right way to draw this. Let's redraw that. I know what's going to happen with my cantilever beam is I'm going to put my load here, and this section is straight. That has no curve. Why? Because there's no moment there. There's no moment on the beam past that point. So that is straight. So I'm going to get a deflection from here to here, which is delta. And that delta, I can go back to my equations. Delta, you'll see it in the middle. The maximum deflection is PL cubed over 3EI. It's downward, so that's why it's negative. Equals PL cubed over 3EI. And then this part where there's no curve, well, whatever the angle is here, theta, this height that deflection is equal to theta times L. Now, I'm using L interchangeably because now this is L, and this is, well, this is that L, and this L is that L. So we can't do that, but that's what we need to do. So we've got to be very careful with our variables, and we're going to have to go back to our figure to really figure this out. It's 3 meters to the distributed load, so this is equal to minus P, which is 25 kilonewtons, times the length that's out there, 3 meters, 3 meters cubed over 3EI. All right. That comes from, that's the PL cubed over 3EI. And then this theta L, well, that's equal to, first I ought to know what theta is equal to. So theta I'm going to drop into this bracket. I go back to my equations, and it gives me the slope at the end. So it knew that I was setting up for this. That is P, it's a negative PL squared over 2EI. And here's where I was going to get sloppy, is I was going to write L there. But this L, those aren't the same L. So I'll call this L1, L2. And then let's rewrite that. Minus P, L being the 3 meters. Sorry, I'm going to put the P right in there. I'm going to substitute my values other than EI. Minus 25 kilonewtons, 3 meters squared, divided by 2EI. I've got to slide this over so you can see it. Divided by 2EI. And then I need to multiply that by L2. L2 is that second distance. I got to look at my figure. Total is 5, so this is 2 meters. Now, if you look, the units that I've got here so far, kilonewtons, meters cubed, kilonewtons, meters cubed, all divided by EI, so I'm okay with that. And honestly, I've got one more term that I've got to put into that, and that's this equals minus, what was my distributed load? 7.5 kilonewtons per meter. 7.5 kilonewtons per meter times the length. Now this is the full length, so that's the 5 meters to the fourth over 8 EI. All right. Let's summarize here, because we're going to put this all together now into one big answer that's comprehensive. I took, here's our overview of the problem. I took this beam, which had, oh, sorry, I was going with a distributed load, and I grabbed the wrong color. I grabbed the color for the point load. I have this beam with a distributed load and a point load. And I converted that to a cantilever beam and a cantilever beam with a point load at the end. And then, and that had two components. That had two components. It didn't have, so it didn't have it at the end. Because I was going to say I have a deflection at the end and then I have an angle, but that would have given me another. That broke into this plus this theta L for this distance. Does that make sense? This was, you know what we did. It's hard. I'm not sure how to conceptually draw that, because really we had that, where that's straight, and this deflection is delta equal to PL cubed over 3EI negative, and this deflection here is equal to theta L. Theta L2. And maybe I got to go there's my L2. And this is my L1. All right? Now, if I write down all those equations, the total deflection is equal to, I kind of needed to do that, but that's okay. My total deflection is equal to, I'm going to do this in sorry, I'm going to try one more time. It's equal to the deflection from the distributed load plus the deflection from the point load at the end plus distributed from the point load angle and then the extra length. So now I'm going to write down each term, delta is equal to, okay, so from the distributed load, I go all the way back to the top. I got it right there, minus 7.5, you know what? Copy. This never works quite right. I think you and I should both have learned this by now. Paste. Circle that. Okay, maybe I'm getting better. Maybe I'm developing some skills. Plus, I've got the deflection from the point at the end, and that's this term here. Copy. Paste. That. Plus, I've got the last term, which is the angle and theta, which is this one here. Copy. Oh, I want to paste it here. If I try to paste it where I want it to go, then it always screws up, or then I always screw up. So there's that. Now let's let me throw in some calculator. The other thing I'm going to do is go back to EI is equal to, E is 28 GPa. E is equal to 28 gigapascals, and I was equal to 500 E negative 6 meters to the fourth. So I can multiply that through. And now I'm going to look at all those terms, and I'm going to come up with delta is equal to, and I'm going to have three different terms and an answer. And the reason I want to do that is I want to compare where my deflections are coming from. And I want to look at how each of those terms, because I want you to start getting a sense for, wow, here's a big contributor, here's a big contributor, or here's a small contributor. All right, so calculator skills time. There you go. All right, so here we go with some answers. So I did this in two steps. First, I calculated just the angle theta, and then I multiplied it by, I guess we're calling it L2, whatever, so that I'd have that in its own little, and I could look at that angle separately. In fact, hold on. Let me, hold on, one more. Yeah, I just wanted to convert that because I wanted to do the angle separately so that I get a sense of it, but I don't have a sense of radians. I can't tell you what a kilonewton is. I can't tell you what a radian is. So I had to calculate that, and that is 0.3 degrees. There's a decimal point there. It's a fraction. It's a third of a degree, and yet it contributes 16 millimeters to the total deflection of the system, and that's, I think, quite a bit. Now, what caught me by surprise was it's exactly the same as the deflection caused by the point load. And the reason for that was the way that the values were picked. There was a 3 that shows up in this equation. That's an extra 3 then divided by the 3, whereas in the theta equation, it's divided by 2, and the distance was at 2 meters. So they kind of set that up so that the deflection from just the ongoing angle is as much as it is from the load at the 3 meter mark. So 2 meters of continued angle created more deflection. Then what caught me as interesting is this the distributed load. The distributed load is just over half. It's about 60% of the total deflection. But then I went back to the problem statement and looked at 7.5 kilonewtons per meter times 5 meters. This load was 37.5 kilonewtons, where this deflection was caused by 25 kilonewtons. So some of this load distributed out at the end has a ton of effect, but the stuff distributed at the beginning doesn't have nearly as much. So there's a balancing act there. But we wind up with, I would say in a fairly straightforward way, we've got a deflection of 0.074 meters. So interesting in how these two terms balanced out, that if you apply the load 60% out, then you get an even distribution of deflection from the bending angle as well as deflection just from the load at the early spot. And maybe that's completely artificial anyway, because why do we care about the deflection at 3 meters other than that's where the load was applied? But I think I don't know what the length of this video is going to be, but in the neighborhood of 10 minutes. And I think you can see this is a quick way, relatively quick, but it does take creativity at the front end to come up with how we're going to add these things together. So anyway, there's our answer. I hope you're doing well. Don't worry, there's more to come.